It is a real pleasure to be here. Obviously, Monash will never really stop being my home. It's where I did my undergrad, where I came back to do my PhD. It is really wonderful to be here talking to you all this afternoon about the work that I've been doing for the last 12 years. So this is going to be a little bit of an unusual talk. So normally people come here and talk to you about science. I'm going to be talking about a little bit of science, but I'm going to be talking a lot about how this project started very small, how we've grown it, the kinds of methodology we've employed to make sure that the resources we've developed to engage diverse communities have been on point, um, and just some of the do's and don'ts really of interacting with the kinds of audiences that we want to reach with this project. Um, so let's see, can I move forwards? There we go. So I always start these talks off with a statement, and this is something that you all know, but it's always worth reinforcing, in that astronomy is a really, really visual science. It's probably, I would argue, one of the most visual sciences out there. Everything we do, from the way we research, the way we receive and analyze our data, the way we communicate astronomy to the public, the way we educate people about astronomy, is all really, really steeped in the visual. The common sort of community perception of astronomy, the way that the average person thinks about astronomers, is this picture of somebody sitting in a field looking through a telescope at the night sky. Or they think of those beautiful full color images of things like galaxies or nebulae or other things like that that NASA and the other space agencies like to produce to really get people enthusiastic about space. And so for that reason, people who are blind or low vision can often find it very, very difficult to engage with astronomy to the same level that their sighted peers might be able to. It's not impossible. There are a handful of people like me who have gone on to become professional astronomers, but we are very few and far between. And it is because there are just an awful lot of barriers along the way to get there. So I wanted to give you a little bit of background about me, just to sort of set the scene for this project, some of the motivation for it, and how I've ended up where I am working on this type of thing. So right now I am an outreach and public engagement fellow. So I'm an astronomer by trade, obviously, but now I'm working in that sort of outreach, public engagement, education space. But back in the day, I did do a lot of work around galaxy evolution formation through the lens, I guess, of things like galaxy luminosity functions. Taking a step back in time, though, so this is me at age 5. You probably see that I'm wearing incredibly thick glasses. Um, so I was born in rural Australia, lots of access to really, really clear, dark night skies. As a child, I would go out and do my best to see what was going on up there. But a lot of that was actually a shared experience. So I would go out with my family, with my parents, with my brothers. I would make out a little bit of what was going on, and then they would fill in the gaps by describing the rest of it to me. So this sort of family stargazing became a real collaborative experience for me. It wasn't something I could do on my own, but with the help of other people, it was something that I could experience alongside them. And so the reason that I couldn't see so much of what was up there is because I was actually born legally blind. So I was born 3 months earlier than I should have been. From that young age, because of those sort of collaborative experiences, because I was surrounded by that sort of, let's go out, let's look at the night sky, space was something that always really fascinated me, that I was always really, really interested in. I was really lucky in that when I said, hey, when I grow up, I want to be an astronomer, nobody turned around and said, oh, you're going to find that a little bit difficult if you can't see what's going on. And so I kind of just went for it. I didn't really know any better, didn't know how difficult it was going to be. And so I chased that dream. Okay, so when I was little, so this was back in the 80s, 90s, there weren't a lot of accessible resources out there to help me learn what I needed to learn to become an astronomer. And so I was lucky again that I had some really passionate teachers, really passionate friends who were really good at working out what I needed and working with me to create different ways of accessing the information that I needed to, things that were a little bit different from what the rest of my class might have been doing. That, I think, has helped me become a really, really good problem solver, help me think outside the box, help me realize that maybe the standard way of doing things isn't always the best way, and that sometimes we do need to come up with slightly different ways of doing things. So bear that in mind as we move through the rest of the presentation. I might have a PhD in astrophysics now, but it definitely wasn't straightforward. So I actually started a PhD and quit after 2 years. Some of that was because I was diagnosed for the first time with anxiety and depression, but a lot of it was also around access. So there were a lot of things that I was trying to do that I was really, really struggling with. I had gotten a little bit cocky by that stage, and I had stopped asking for help when things were getting really, really difficult. I thought I could do absolutely everything on my own. It took a lot of soul searching, a lot of me realizing that it was okay to ask for help sometimes, but it was also really, really good to push on and try to do those difficult things on my own when I could. But basically, with the first PhD, things hit a crunch point. I got really frustrated. I quit. I went away. I did a few other things for a couple of years, and then I was lucky enough to meet Michael. He offered me a second chance to sit down and try and do that PhD again. And the second time, I managed to get through. So during my PhD, because astronomy is such a visual subject, I had to lean into a lot of really visual elements, and some of those I didn't always find particularly easy. So this is an example of one of the luminosity functions that I calculated as part of my PhD work. The actual science of this, what this plot is, doesn't really matter. What I want you to focus on, though, is the design choices that I've made when producing this plot. So I started off making plots and diagrams to communicate the science that I was researching that looked like the plots that everyone else was making. They had tiny captions, they had tiny text, they had really difficult to make out points on plots. They were generally black and white, not a lot of colors involved. It actually took one of the other astronomers working at Monash at the time, Heath Jones, turning around to me at one point and saying, Nick, can you actually see the plots that you're making? And I said, well, no, but I'm making them for other people. He said, no, no, you're not. You're making them for yourself as much as you're making them for others. So make the kinds of plots that you can see, and everybody else is just going to have to get used to the way that they look. And so I took that on board. I started making the kind of plots that I wanted to see that I could make out easily. So lots of really big font, really bold text, lots of distinct colors, distinct symbols, just everything I could possibly do to make my plots a little bit easier to see. And yeah, that was sort of a bit of a turning point for me, realizing that I didn't have to do things the same way as everybody else. I could do things that worked for me and kind of force everyone else to just get used to it. Where I did run into some issues though, so my PhD involved dealing with a pretty big data set. So I was studying over 13,000 galaxies in our little corner of the universe. Um, I had numbers for a lot of different parameters for those, everything from their size, their distance, uh, their current star formation rates, their morphologies, all these kinds of things that could be represented with numbers. Occasionally, though, I did actually have to look at images of these galaxies to make sure that the numbers, the data that I had was actually telling me the right thing, that it wasn't in contrast to what the telescopes pointing at these objects had actually seen when they'd observed them. And so I got an example of some of the galaxies that I was studying on the left here. Now, most of you can probably see these pretty well. You can tell that it's a mix of spirals and other morphologies. For me, though, this wasn't always particularly easy. Actually, looking at these images, seeing enough of them to do that cross-checking to make sure that my data wasn't lying was actually a little bit difficult. And so when I first moved to Portsmouth, I met a couple of really interesting people, had a few chance conversations. One of the questions that was asked to me early on was, well, if you found this part of your PhD so difficult, what could you have done to make it easier? And my almost instant response without really thinking was, well, if I could have made my images tactile, if I could have felt them instead of having to peer at them and try to make out all that detail that I couldn't really see, that would have made my life so much easier. And so that was sort of the birth of the Tactile Universe project. So the Tactile Universe is a multi-award winning public engagement project, which we started all the way back in 2016, so just after I'd moved to the UK. As much as possible, we try to use real data to create tactile and audio resources that can create more accessible ways for blind and partially sighted people to access current topics in astrophysics research. And so that's what the rest of this talk is going to be about. So the main goals of the project are pretty straightforward. What we really want to be doing is working with the blind and low vision community to create the resources that they want and that they're going to find useful, covering everything from education to outreach to research. Oh, sorry. Problem with being blind is sometimes you forget what's on your own slides. So we also want to build interest in science with blind and low vision students from a young age, using our resources and using the tools that we're creating to show them or demonstrate that science, things like astrophysics, physics can be accessible and that they don't need to feel like they're locked out of those subjects. We also want to work with as many other groups as we possibly can, particularly researchers, public engagement experts, educators, to help them make the science that they want to communicate more accessible. And last but not least, we really, really want to get the point across that accessibility helps everybody. Even though our project has a really particular audience in mind, we have shown time and time again that these resources don't just benefit that audience, that everybody can get something out of these. If we can give people a different way to access something, something more than just visual, if we can allow them to touch something, to listen to something as well as that, we're increasing the ways that they can take information in and we're making things better for everyone. Okay. So even though I'm the one giving this presentation today, I am part of a small team who's working on this. So the core team are myself, so I lead the project. I also work with Professor Jen Gupta. So Jen is a professor of public engagement in astronomy. She leads the public engagement group in our department, so I work directly underneath her. She is the one who came up with our model basically for expanding the project beyond its really, really initial small scope. And then we have Coleman Kruzek. So Coleman's an astronomer by trade. He did his PhD studying AGN in the US. He's now one of our department's research software engineers. So he basically takes other people's coding problems and solves them for them. So we have quite a big group of research software engineers, but he's also our 3D printing expert. So he runs our 3D printers. He also came up with the original software plugin that we use to make our tactile images. And I'll show you a little bit about that in the future. Later on in the talk. But we've also worked with a few of the other people at the ICG where I work as well. So Laura Nuttall, who some of you might know, is one of our gravitational wave astrophysicists. And we've also worked with two past PhD students, Connor and Simone, who've helped us with a couple of things, particularly in relation to communicating gravitational waves. Okay. So linking back to this idea of astronomy being really, really visual. So up on the screen here, I've got a Hubble Space Telescope image of the galaxy Messier 51. And I would argue this is one of the most beautiful images ever captured by a telescope. You could spend hours and hours looking at this. It has so much detail. You can see everything from the regions of this galaxy where there are colder, redder stars, the arms where there are hotter, younger blue stars. You can see the gas and dust winding its way out from the center. You can also see the little companion off to the side there being stripped by the larger spiral in the center. You can see almost this sort of feathering in the arms where the gas is being shaped by the star formation, supernovae, all kinds of things like that. So this is an incredibly complex image. There's a lot going on. And it's something that takes a lot of words to describe to somebody. So if you can't see this image, it's actually a really, really difficult thing to access. So we came up with a really, really simple idea for this. Basically, what we wanted to do was create a tactile analog of an image like this that somebody could run their fingertips across, get the same information about shape, about brightness, as they would if they were to look at the image. And so building on what I said before about the initial conversation that I had, where somebody asked me, what would have made your PhD research easier? My response was, well, if I could make things tactile, that would be fantastic. Coleman actually overheard that conversation. He had a little bit of experience 3D modeling, and he took my basic description of what I wanted to create, went away, and 2 days later, he came back to me and he showed me a digital model that he created. And he said, Nick, is this what you were talking about? And I said, oh my God, this is fantastic. It's exactly what I wanted. We then found somebody with a 3D printer and they 3D printed that model. And when I felt that model, that was the first time that I had really understood Messier 51 as a galaxy. It was absolutely mind-blowing, really amazing. But the basic method that Coleman used here is he took a black and white image like the one on the left. So this is a telescope image of M51. This is actually from the Sloan Digital Sky Survey. To translate it into this tactile surface, we basically assign each of the pixels in the image a different height based on how bright they are. So the whitest pixels sit the highest above the base of the model. The blackest pixels sit as low as they possibly can, so basically flush with the base, and then every other shade of gray scales in between. And so we end up with this tactile surface that very much represents that image that we started off with. Okay, so we had this basic idea. We'd managed to 3D print this tactile version of this image, and we thought it was pretty good. But we realized very quickly that even though I'm somebody with a vision impairment, what worked for me was not necessarily going to work for everybody else that we wanted to try and get these models out to. And so this is where co-creation comes in. You can come up with the best idea ever, but it's never going to be quite as good as it could be unless you engage the audience that you actually want to develop this thing for to make it better. The reasons for that are that particularly with disability, there's no one size fits all. So everybody has slightly different needs, slightly different things that might work better or worse for them. And so for that reason, if you can make a model that's really, really versatile or a resource that's really, really versatile, you're more likely to make something that's going to work for more people. The other just simple fact is that somebody who's had a disability for their entire life is really going to be their own expert on what they need. And so assuming what somebody needs can be really dangerous, but actually asking that person, getting them to tell you what works, what doesn't, can be really, really valuable because they'll save you a lot of time and effort, and you'll make something that is going to work much, much, much better. So with that in mind, with our original prototype, we wanted to basically try to work out what parameters were going to work the best for our blind and low vision audience. So we created a whole bunch of models that had different tactile heights, that were different sizes, that had a few different sort of extra features built into them. And we took them out to a community group that had about 20 blind people, mostly retirees, so slightly older, but a few younger people as well. And we got them to play around with our models and basically tell us what worked. We also ran a community event where we invited people to come and spend a day with us learning about galaxies and astronomy. And again, we tested the models, but we also started to think about the kinds of language that we wanted to use. And so it might not surprise you, but it turns out that a lot of the analogies that we use to describe astronomy, particularly to the public, can be really, really visual. They rely on things that people have seen to sort of build that relationship with something that might be a bit more abstract. And so we actually had to start thinking about how we could tweak those descriptions, tweak those language, or that language that we were using to make it more accessible, to make it more relatable to people who had no vision or low vision. We also spent a lot of time learning how to 3D print by failing. And so on the left, I've got a picture of a 3D print where basically the outer layer hasn't printed properly. And so someone's gone to touch this and their finger's gone straight through. The picture on the right-hand side is what a 3D print looks like when it falls over after the first 5 minutes, but you don't realize and you let it keep printing for 20 hours. So 3D printing is great. It is a little bit of a learning curve to get it going properly. But yeah, we very much learned by failing. Now we print some really, really amazing stuff, and stuff only fails some of the time. But these are the final models that we settled on. So on the left, I've got a picture of the front of one of the models. On the right, I've got a picture of the back of one of the models. And I'm just going to go into both of those sides just to explain some of the design choices and how that was influenced by feedback we got from the people that we tested these with. Just to note as well, I do have a whole box of these models with me here. So when the talk's finished, if you want to interact with any of these to actually feel what they're like, we're going to be able to do that as well. But I'll do my best to describe them for the time being. And I'm not going forwards. What has gone wrong? Okay. There we go. Okay. So the features of the model, so just the general size and the depth of the tactile features that we settled on. So we ended up making models that were about the size of a postcard. The reason for this is they're really easy to handle. You can pick them up with one hand, with two hands. You can sit them down on a table really easily. You might intuitively think that producing a bigger tactile model is better. In this case, that's definitely not true, though, particularly with something as complex as an image of a galaxy. The problem with making a really big model is people tend to get lost. They get lost in the detail. They can't work out where they are. So lots of reasons why we need to make these a little bit smaller. In terms of tactile height, we settled on about 3 millimeters. The reason for that choice is because for an image of something like a galaxy, which has quite a range in brightnesses, 3 millimeters is enough to really emphasize those changes in brightness across the model without the model becoming too sharp and unpleasant to touch. Anything lower than that, and it actually became really hard to feel some of the detail in the image as well. So 3 millimeters, at least for galaxies, is kind of the sweet spot. So looking at the front of the image first, so this is where we have our tactile surface. We also have a raised border around the edge of the image, and we have a tactile nameplate attached to the top. So all of these design choices, the raised edge, the tactile nameplate, came from feedback that we got from people. The raised edge around the model is actually as high as the brightest point in the image. So it's actually a way for you to calibrate what you're feeling. If you want to work out how bright any part of the model is, you can basically span your hand or your finger from the edge to the bit that you're feeling, and you can work out sort of, yeah, whether you're feeling a really bright or a really dim part of the image. It also helps people not track all the way off the side of the models and have to sort of find their way back again. The nameplates have sort of two main functions. So they help people identify what model they're interacting with, but they also help to orientate that model. And you'll see why that's important in a second. So we actually don't just print these in a single color band, we print them in multiple color bands. So if people want to move between those same images of the same galaxy, having that feature that helps you orientate the image is actually really, really important. Flipping over to the back of the model, this is actually something we would never have thought of ourselves. Initially, we just made the models tactile, but we were actually working with somebody who was partially sighted, and they said, well, I can see a little bit, so I really want to use my eyes as well as my fingertips to interpret these. What they wanted us to do was embed the image inside the model and make the model transparent, which we didn't have a way of doing at the time. What we did instead is we mirrored the image and attached it to the back of the model. And so the idea being here that you can look at that image and you can feel the corresponding tactile features on the other side. And so if you're somebody who can see a little bit or see a lot, and you want to use that to supplement what you're feeling with your fingertips, it's just a really nice way of making these models multimodal to make them even more accessible. But that was very much something that we didn't come up with ourselves. It was only because we tested these models and we got that really valuable feedback from people that we were able to come up with that particular idea. Okay. So I kind of touched on this before, but descriptions and analogies are also really, really important. So many of the things that we use to describe celestial objects like galaxies are really, really tied to the visual. We fell into the trap initially when we wanted to talk about our galaxies we referred to them as blue or red, but without any kind of context. And one of the completely blind people put their hand up and said, I've been blind for my entire life. Color means nothing to me. What are you actually talking about? And so we took a step back. We had to think about things, and we realized that it's actually much more valuable, and probably something we should have been doing anyway, to actually link that color to the physics. So in this case, the color of a galaxy is very much linked to its stellar population. If you're seeing red light, it's coming from older, cooler stars. If you're seeing blue light, it's coming from younger, hotter stars. And so establishing that language link so that if we did slip up and just say this galaxy is red, this galaxy is blue, the people that we were talking to were going to go, he's talking about hot stars or cold stars. We can also lean into lots of other analogies to talk about things like shape as well. So the whirlpool galaxy is a prime example. You can't reach out and touch a whirlpool. So that can be quite an abstract thing to throw at a blind person. But there are other things that are shaped like that, things like snail shells, pinwheels, even just describing a galaxy like a cloud and then linking that cloud to the idea of walking through the mist on a misty morning can be a really nice way of using a slightly more relatable analogy to talk about something like a galaxy. Okay. So that's the end of the pilot. So we had some really basic galaxy resources. We knew that they worked with the community that we wanted to engage with, but we also realized that we wanted to reach a lot more people than we'd been able to just around Portsmouth. So we applied for some Science and Technology Facilities Council, which is the sort of science funding body in the UK. They run awards for public engagement projects. So we applied for one of those. We were successful after our fourth try. Oddly enough, one of the bits of feedback the first time we applied was, we don't think this is going to reach enough people. which was a bit sad, but obviously we managed to convince them eventually. So they gave us funding. With that funding, we were able to change our focus a little bit. So rather than trying to engage everybody who was blind and visually impaired or blind, partially sighted, we decided we really wanted to focus on students in school settings. There are two reasons for that. So number one, when you go into a school, the students have to be there. So you have a captive audience. The other thing is that there's lots of research that points to the fact that if you can engage students positively with science at a young age, and you can do it over the course of several interactions, so not just coming in once and going, wow, space is great, and then hoping that that kind of sticks. If you can come in again and again and again and keep inspiring those young people, they are much more likely to move forward into adulthood with a positive outlook on how useful something like physics or astrophysics might be. So we switched our focus a little bit. We started working with students in local schools. We went out to do several sessions with them to show them our models, to talk to them about what they wanted out of a classroom experience using those resources, what they actually wanted to learn about, and also to make sure that our analogies were going to work for them based on where they were in their schooling. We also spent a lot of time traveling around the UK training other people to use the resources that we developed. We went to Wales, England, various parts of England and Scotland, trained around about 66 different people. We also produced a whole bunch of physical resource kits to send out to those groups so that they could start delivering our project to the students in their local schools. Alongside that, we also made a website. We put all of our models that we'd already created on there so that anybody with a 3D printer could download them and use them themselves if they had access to that. We also shared lesson plans that had analogies that we'd come up with. So basically full scripts that people could use if they wanted to sort of get a bit of help in working out how to run these workshops. We also produced 3D printing guides, and we released the software plugin that Coleman had created to make our models. The idea being that anyone can use that to create a tactile version of any image that they have. So basically you can feed any black and white image into that. It'll create a tactile surface, and then you can 3D print that. So we really wanted to make sure that anyone, anywhere who wanted to use our stuff could do that. So in this first round, we really wanted to focus on late primary and early secondary, because in late primary, students already learn about the solar system as part of their space topic. We made our first workshop all about the solar system. We then used our galaxy resources to make a second workshop about galaxies. For students in lower secondary, we made another slightly more advanced galaxies workshop where we dive into a little bit more of the physics around what gives galaxies their shapes, how galaxies can change over time, why particular galaxies are particular colors, all kinds of things like that. These workshops generally last around about an hour, and they're quite versatile. So we can either deliver them to smaller groups of blind and low vision students, or we can deliver them to mainstream classrooms where there might just be one blind student. The really nice thing about that second option is we can get everyone in that classroom working together at the same time using the same resources. This has actually been really positive because a lot of the time we've heard back from the teachers after we've been in, and they've said things like, so-and-so student has started hanging out with some of the other students in the classroom after you've run your workshop, or the other students in the classroom have started asking the blind student about how they access the world and what's going on. So really what we're trying to do there is break down barriers, promote understanding of access. So that's been really, really positive. So in terms of resources, for our solar system workshop, we went pretty low budget, pretty low technology. We focused mostly on the sizes and scales in the solar system. So for the sizes, we have a collection of seeds and balls that represent the scale sizes of the planets in our solar system. So everything from a peppercorn to represent the Earth, up to a tennis ball to represent Jupiter, and then a giant beach ball to represent the Sun. We then do an activity which we stole from somebody else, but modified to make it more accessible, where we have a long strip of paper. Students fold that multiple times to mark out the positions of the planets in the solar system, and they build basically a scale map of the solar system reaching all the way from the sun out to Pluto. To make that one accessible, rather than getting students to mark the planets with a pencil or a pen, we get them to stick down rhinestone stickers. So there's little jewel stickers that you can buy off Amazon or eBay. And so that means that once they've built their map, they can run their finger along and really get a sense of how the planets are spread out. We then build on that information to start expanding ideas around the size and scale of things beyond our solar system. So we have a really simple tactile diagram that represents the patch of sky around the constellation Orion. So this we can use to sort of build up the idea of what the night sky looks like. We then have an edge-on tactile image of the Milky Way galaxy that we can use to start talking about where we are inside the Milky Way and why we see it the way that we do. We then get students to build their own model of a spiral galaxy like the Milky Way using a CD and some Play-Doh. And so the advantage of this is it starts to teach the students about the kinds of shapes that galaxies have so that when they move on to our more complicated tactile images that are produced using real data, they know what to look out for and they know what kinds of shapes they're going to be encountering. And so then we've made 10 different sets of tactile galaxy images. It covers a really, really wide range of different morphologies, everything from really smooth elliptical galaxies to edge-on spirals to flocculent spirals, really tightly wound spirals, a pair of interacting spirals. I love the irregular galaxy because it looks like somebody's just sneezed a whole bunch of stars across the night sky. And we even managed to slip a red spiral galaxy into that mix as well. And then to deal with the issue of color, because that is an important thing that we want to get across, is that these galaxies have different stars inside them and that makes them different colors. We actually, rather than trying to represent that in a single image, which would have been a little bit complicated, we actually decided to fall back on the way that telescopes actually see these galaxies. So I know we probably have a few folks in the room who aren't astronomers. So the way that telescopes image space, image galaxies, is we tend to put filters in front of those telescopes that basically isolate particular ranges of light. So the idea being that if you want to look at the blue light coming from something, you put a blue filter on your telescope and it will just pick up that range of wavelengths around blue. So the way we actually make the full color images that we tend to show to the public is we take blue, red, and green images and we stack them on top of each other. And so that's why they're called false color images. It's because we're not actually taking an image of that galaxy in full color. We're using those individual filtered images and then stacking them. So what we've done with each of our galaxies is we've produced a blue light and a red light version just to really emphasize what those different stellar populations in those galaxies look like. It also really changes the tactile feel of those models as well. And hopefully if you stick around to feel some of the models after I finish talking, you'll be able to sort of experience that for yourselves. Okay. Oh, sorry, just to say what we do with these images. So for the primary school students, we get them to do a sorting exercise where they come up with their own classification scheme based on the shapes of the galaxies. For the slightly older students, we do that activity, but then we also dive a little bit deeper into galaxy morphology, galaxy evolution. We kind of have enough different kinds of galaxies here that we can really start to talk about how one galaxy might change shape over time, how we end up with things like elliptical galaxies or irregulars or red spirals. So there's a lot of really nice science we can talk about. Okay. So after that, we were lucky enough to get a second round of funding. So what's called a legacy award, which is basically designed to allow people who've gotten one of the public engagement awards through the STFC to work out a way to carry their project forwards even more. You might notice the span of years that this part of the project covers. So this was 2020 through to 2023. Can anyone tell me what happened? Yep. So most of you probably have a blank where you don't remember very much. I certainly do. So this spanned the pandemic. Definitely made some aspects of the second part of the project a little bit more difficult. We definitely didn't have access to anywhere near as many people to test things out on. But what we aimed to do with the second part of the project was develop some resources that we could use with older students, so students in the last few years of their secondary education, to talk to them about gravitational wave astrophysics. Ooh, yeah, because some of the physics involved with this is a little bit more abstract, we also wanted to create some resources that tied directly back to what the students would have been learning in their core science lessons. So covering topics like waves, gravity, forces in motion, just to make sure that even if those students had learned that stuff, that we were reinforcing that knowledge before we jumped into talking about gravitational waves. And at the end of this, we also trained the LIGO research group in our department, but also three of the other LIGO research groups around the UK. So the group in Glasgow, group in Birmingham, and the group in Cardiff in Wales, to make sure that they could use these resources. And we also left physical resource kits with them so that they could start to use those with students closer to them as well. And so you might be wondering why gravitational waves? Well, number one, gravitational waves are really, really cool. There's a lot of really nice physics tied up with how they work. They're really fun to describe. One of the issues we find, though, of course, is again, people tend to lean into the visual. So here I've got just a really quick movie. So for anyone who's not an astronomer in the audience, gravitational waves are technically produced by anything massive that's accelerating through the universe. They're literal ripples in the very fabric of the universe that move outwards from that object. The only gravitational waves we can currently detect on Earth come from things like binary black hole systems or binary neutron star systems, where we have really, really dense compact objects that spiral in towards each other. As they're spiraling in, they're accelerating. So that throws out gravitational waves throughout the universe. If those gravitational waves pass through the Earth, we can use detectors to pick them up. But those detectors themselves are really, really, really amazing just in terms of how they work. But if we want to describe this to the public, we usually show them a really nice video like this. Let's see whether I can get that working. So on the screen here, we've got two black holes spiraling in towards each other, and we have the waves spiraling outwards from them, traveling out into the universe. As they collide, we have a final thing called a ring down, where the waves get really, really close together, really, really sharp. Again, if you're someone who's blind or vision impaired, you probably can't see a movie like that. So we come up with some novel ways of communicating the information that we want to. For this part of the project, we also lent into some audio resources as well as tactile resources to make things even more multimodal. And I'll show you how we did that in a second. But for this, we've created three separate modules. These last about 20 minutes each. We went for slightly shorter this time just because the content is a lot heavier. There's a lot of information to absorb, and the physics involved is a little bit more complicated. Yeah, so a big emphasis on reinforcing those core topics to make sure that we're not leaving anybody behind with any of our descriptions. We structure them a little bit like conversations. So we really encourage the students to ask lots of questions, to speak up at any point if stuff isn't making sense. That can be a little difficult if you don't know the students and if the students don't know you. So it can be worth spending a little bit of time talking to them about other stuff first. Again, these work really well with smaller groups of VI students, but we can do them with slightly larger groups of VI and sighted students as well. But the problem with working with bigger groups is people are less likely to speak up and ask questions, and that can definitely detract from some of this as well. So the three modules. Initially, we wanted to focus on describing the compact objects that actually produce gravitational waves in the universe. So we really wanted to talk about things like white dwarfs, neutron stars, black holes. We made a whole series of resources to talk about this, everything from really low tech to slightly higher tech. So on the top left-hand corner there, I have three balls. These are all identical in size, but very different in weight from each other. So I have a ping pong ball, a squash ball, and a heavy metal ball bearing. These actually scale by a factor of 10 each time. So it's a really nice example of how mass increases very rapidly when you start multiplying stuff like that. It's also a really nifty prop for people to hold in their hand. We can do really crazy things like say, so if you're holding a ball in your hand, if that was a black hole, it would weigh as much as the entire Earth. Or if it was a neutron star, it would weigh as much as an entire mountain range. So it's a nice way of just making that information a little bit more tangible. We also have some high contrast 3D prints that we've made that demonstrate really simple things like how objects move around each other in space. So the three on the top right-hand corner of the screen are supposed to represent what would happen if something went past something really massive in space going slowly, so it would crash in. Going past slightly faster, it would never actually happen, but let's assume it would drop into a circular orbit, or going past really, really fast, and so it would just have its direction changed. So we can use this to talk about Newton's ideas of gravity as well as Einstein's ideas of gravity. Lastly, for this one, we also have our own little tabletop version of the stretchy spacetime demo that half the gravitational wave community seems to think is fantastic and the other half seem to think is the worst demonstration possible. So this is meant to demonstrate orbits, but also demonstrate how masses distort the space-time around them. So the idea is you have a stretchy bit of fabric. You can drop massive objects into it to change its shape. If you drop something really heavy into the center, you can make something slightly lighter orbit around it. The really nice thing about this being as small as it is, and I'll show this at the end as well, is students can actually put their hands underneath and they can cup the underside of the surface. And if you orbit something on top, they can actually feel it moving. So it's a really nice way of turning what's otherwise a really visual demonstration into something that's much more tactile. Yeah, so in this initial one, we really focus on those compact objects, explaining how white dwarfs, neutron stars, black holes are formed, and talking a lot about gravity and how Newton and Einstein understood those two things. Next, we move on to the detection of actual gravitational waves. And so on the left, we produced a really, really simple tactile diagram of a sine wave where we've shown two of the different parameters. I believe it's the amplitude, so the height of the wave, and the wavelength. So again, this is just to really reinforce what waves are, make sure that students have all the right language in their heads when we start talking about things like amplitude, frequency, intensity, other things like that. To talk about gravitational waves themselves, we've also created 3 snapshots of a binary black hole system basically in spiraling, so those black holes spiraling in towards each other, and the resulting gravitational waves moving outwards from the center. And so we can use these to basically talk through that process, how the waves change over time, how they get stronger and stronger and closer together as those black holes get closer and closer in orbit faster and faster. My personal favorite here is the ring down, where we have the super, super close together burst of waves just as the black holes collide at the end. One thing about that, though, that description and using those models doesn't really get across just how quickly a gravitational wave event actually happens, or at least the bit that we can detect here on Earth. So we've also paired that with the audification, or the basically the gravitational wave signal turned into sound that was released alongside the press release for the very first detection of gravitational waves. And so I'm just going to play that really quickly. Let's see whether it works. So did you all hear the little whoop? Kind of a bit of an anticlimax, if you ask me. But what this does is actually gives people a temporal sense of what's going on. So when we describe this using these models, people assume that it takes thousands of years or hundreds of years for all of this to happen. And that's true to some extent. These systems can spend a really, really long time evolving. But the actual bit that we can detect with our gravitational wave detectors, particularly for that first signal that we ever found, actually lasted for about 0.2 seconds. So really, really fast. And so the great thing about adding that audio element is it gives a temporal sense of how these systems evolve. So you're adding that extra information by using that different sense. So that's how that one works. Finally, we wanted to really talk about gravitational wave detectors because, of course, they are amazing bits of equipment. I still can't quite believe that we've built something as sensitive as this, and that we're even able to detect gravitational waves in the first place. So again, for the non-astronomers in the room, the way these work is LIGO as an example, is basically an L-shaped observatory. It has 2 long arms that stretch for about 4 kilometers. They actually have to be propped up at their ends so that they remain straight, so they don't follow the curvature of the Earth. The idea is you then fire a laser down each of those arms, and there are mirrors at either end that basically bounce the laser backwards and forwards so that you can simulate the arms being much longer than they actually are. When a gravitational wave passes through one of those arms, it changes the travel time for the laser light. And so what you're looking for basically is an interference pattern when the laser light comes back to the center and meets up again. If one of those arms is slightly shorter, the laser light will be out of phase. So again, you can describe all of this with words, but what we decided to do was make a puzzle piece diagram of one of these interferometers, one of these gravitational wave observatories, that we can get students to build as we talk about it so that they can understand how the laser light moves through and how these things work. We also really wanted to talk about all the technology that goes into these. So everything from the super sensitive pendulums that the mirrors are suspended on, that basically stop them from jiggling when a car drives past a couple of kilometers away on a road, or when there's an earthquake around the other side of the world, or when there's a storm. The technology that's being used to make those mirrors super reflective so that they don't lose too much in the way of photons each time they reflect the light. The way those tubes are kept in almost perfect vacuum. All of that amazing technology, everything down to the computing that we actually use to work out whether we've detected a gravitational wave in the first place. All of that, of course, ties back to this idea of noise. So most of the gravitational wave data that arrives is incredibly noisy, which makes it very difficult to actually analyze. And so we've actually got a gravitational wave signal hidden in amongst a whole bunch of noise that we can use to demonstrate that. So have a listen to this. Did anyone hear the little whoop? It's pretty hard. But there is a gravitational wave signal hidden in there, and you can train your ears to listen out for that. But of course, there's also software that will find that for you as well. But yeah, this is actually the module that a lot of students really, really like, because they really get hooked on this technology and all the amazing things that we've had to come up with to actually detect gravitational waves in the first place. I'm just going to check how we're doing for time. Okay, I'm going to speed up a little bit just to finish. So what are our plans for the future? Probably slightly too many things, to be honest, but there's a lot of work that we can do, and it's all really, really exciting. So Laura Nuttall has managed to get a little bit of extra funding. We're going to use that over the next 2 years to develop just a few more resources to talk about gravitational waves to supplement what we've already made. Laura's also really keen on getting more gravitational wave researchers around the world using our resources. So we're hoping to train a whole bunch of people. We'll probably do that at one of the annual meetings. So if you're going to attend one of those, if you're a gravitational waves person, please keep an ear out for that, because we would love to share our resources with you. We would love to get more people using those. More broadly, what we really want to do is start properly supporting the groups who've taken our resources, who are trying to use them with their own audiences. What we do tend to find is if we don't chase people up, they sort of forget that we've given them resources and they don't use them. So we really want to make sure that folks are doing that. We really want to work a little bit more with specialist teachers to make sure that we're tapping into their expertise, because they really are the experts in education for the audience that we want to work with. So we want to make sure that we're getting as much knowledge from them as we possibly can, that they're inputting into our resource development as well. We've got a little bit of work coming up with some of the bigger museums in the UK as well, where we're hopefully going to help them make their offerings a little bit more accessible. And we also want to support any current and future low vision or blind students who come through our degree at Portsmouth. So we've actually just had one student. He's about to finish his 4th year, his master's year with us. And he's actually been working with myself and another colleague to do his final year project. So we want to make sure that we're set up that if we get more students in the future, that we really know how to make the courses accessible as we can for them. We've also just received even more funding from the STFC to extend the project a little bit further. What we've actually decided we're going to do here is take a bit of a step back from the astrophysics. And what we want to do is focus on the core science topics that feed into the workshops that we've already developed. And we want to make some resources covering those topics that students can use before they start engaging with the astrophysics that we really want to talk to them about. So we're going to be working with a few local primary and secondary schools, the students there, as well as the teachers, to develop those resources. Once we've made those, we want to share them as widely as possible with the BLV education community in the UK and further afield, so that those resources can really get used as much as possible. Really excitingly as well, and this is where I think I'm probably taking on slightly too much stuff, we've just applied to become a node for the International Astronomical Union's Office of Astronomy for Education. We're going to be focusing on astronomy education for the blind and low vision community. Our role there will basically be to help anyone else who wants to do this type of work find the resources that they need, or find the expertise that they need to do the work that they want to do. We want to share our own resources, obviously, but we also want to help other people develop their own stuff. We also want to highlight all the resources that other groups around the world are also developing. So that's going to be really, really exciting once it actually kicks off. And very, very quickly, last but not least, I wanted to talk about another project that sprung up as a result of our project, which is called the Audio Universe. And you might be able to guess, this is a project that really focuses on sound rather than tactile resources. So I'm one of the members of this project, but it's led by Chris Harrison, who's an AGN researcher at Newcastle University in the UK, and James Trayford, who is a postdoc researcher at Portsmouth. James is developing this amazing suite of code for Python, which is called Strauss. He thinks of it as like, so if anyone here is a coder, uses Python and uses matplotlib to produce plots, James is basically pitching this as the equivalent of that, but for sonification. So basically, people are going to be able to take his code, sonify data in any way that they want to, using whatever parameters they think might work. So it's really amazing work. It's going to be really powerful. For education and outreach, we've also done a fair bit of work creating a fully accessible planetarium show, which works completely without visuals. So just audio if you really want it to, but it does have visuals included as well. That's been picked up by a couple of the big planetariums in the UK. So Royal Observatory Greenwich is showing that as part of their regular roster. I narrate that one, so just you're warned if you do want to check that one out. But yeah, that's a lot of fun. We're about to start making a second show about black holes. And just before we finish, I wanted to show you one last thing. Oops, I'm going to skip over that one. So this is, I think, a really good example of how powerful something like sonification can be for analyzing data. James has produced this. This is part of the Calibre, I never say that right, simulation, which is a new suite of hydrodynamical simulations focusing on galaxy evolution from the really early universe through to current times. This is an example of a galaxy evolving over time, and James has mapped 3 separate parameters to 3 different kinds of sound. So we have the black hole accretion rate, so basically the rate that material is falling onto the central black hole in the galaxy. That's modeled onto clicks, and those clicks will get closer together as that rate increases. We have star formation, which is mapped to, Sam, can you remind me? Yep, so harp notes, and the pitch of those and the volume is tied to how much star formation is going on. And then lastly, we have a windy sound that's mapped onto basically material being blown out of this galaxy either by AGN, so jets of material shooting out of the central black hole, or being blown away by things like supernovae. So I'm just going to play a little bit of that. And even though we have 3 parameters all playing at the same time, it's amazing what you can actually hear. So not a lot going on right now. I'm going to jump to a slightly more exciting one. There we go. There we go. So hopefully that gives you an idea of, yeah, how we can start thinking about using things other than more traditional visual ways in research in particular. This, I think, is a really powerful way of really mapping how different parameters are evolving alongside each other, how they're affecting each other, everything like that. It definitely does take a little bit of practice to start listening to everything at the same time and really picking out that data, but I would argue that it's easier than trying to keep track of everything visually. Okay, so that's it from me. Hopefully I've taught you something new today. I'm sorry this talk is so different from what you're probably used to, but if you are interested in finding out more about Tactile Universe, we do have a website. It's tactileuniverse.org. The Audio Universe's website is audiouniverse.org. You can contact me at the Tactile Universe's Gmail account. We aren't really on Facebook, or Twitter's a pretty horrible place, to be honest. So we're not really on Twitter anymore. But yeah, definitely if you hit up that email address, I'll usually try to respond pretty quickly. But yeah, everything we've ever made is online and downloadable for free. So thank you so much, everybody.
Thank you, Nick. And we have time. Oh, we can squeeze in a few questions, I think. So if people online would like to raise their digital hands if they have a question, and then if people in person can raise their hand. And we do have a question online in the chat. Actually, Manisha, I'll pass the microphone to you so you can read that.
Okay. It's from Jing Hu. Great work, Nick. I'm a sighted person studying the humanities, so forgive me if I ask 2 questions. First, apart from images of outer space and core physics concepts, what are other things that you have found inaccessible, real hurdles for VLV astronomy students, researcher? And the second question is, have you come up with ideas to address those barriers? Or how did you cope when you were doing your PhD?
Oh, okay. Those are really good questions. So I think it's hard to know. I think oftentimes as a blind person, it's difficult to know what you don't know until you realize you don't know it. Um, so in vision impaired education, there's something called, oh, well, it's knowledge scaffolding. So this idea that you kind of need to start from really basic concepts and build up information without leaving too many gaps and without assuming that people know all the information that you might accidentally skip over. And so a really good example of that is there was a story from one blind lady that I spoke to who admitted that she always thought that chickens had their legs sticking up into the air. And the reason for that is she'd only ever interacted with a roast chicken. And so that was her concept of the morphology of a chicken, right? So you laugh, but it's also kind of, it makes sense, right? If that's the only chicken you've ever experienced, that is what you think a chicken is shaped like. And so we do have to be a little bit careful, and we need to make sure that we're not leaving those gaps, that we're filling in as much information as we possibly can when we talk about this stuff in particular. Trying to think what kinds of stuff I found difficult. A lot of the time it was, yeah, when people glossed over things and just assumed that I knew something because it was something that somebody else would have just seen and understood, that maybe something that I wouldn't have been able to see. Definitely for me, there wasn't as much in the way of accessible technology when I did my PhD. So now it's a lot easier to get your hands on a really good sort of text to speech or magnifying software. There are things like refreshable tactile displays, sonification, audification is becoming much more prevalent as well. Yeah, no, really good question. Not sure whether I answered it particularly well, but thank you.
Nick's probably conscious of his PhD supervisor looming next to him as well.
Michael was fantastic, and you always helped whenever I stumbled over stuff. So yeah.
And there's another hands up online. So, we've got another question online. Actually, who's this?
This is
Ramona. Do you want to ask your
Yes.
question?
Can you hear me okay?
Yes.
Thank you, Nick, for a great presentation and describing things so well. I'm another non-astronomer in the virtual room, and I'm also totally blind, being vision impaired from birth. I am interested, though, from a lay perspective in astronomy, and I also found that I learn tactually rather than audio. So I'm glad you, one, described things, but two, recognize that every blind person's different. And, I've had that interest. I've even a couple of decades ago bought the books from Noreen Grice, which were, I think, a NASA project on Touch the Stars and then Touch the Universe. And I found those really interesting. But I think 3D printing just makes accessing visual information through that 3D model so much better. And I think my question, you may have answered it in part towards the end of your talk, but I'm wondering how you use 3D to present concepts of motion. So you've talked about shapes and color and the different brightness, etc., through models and images. But I'm thinking of concepts like orbit or orbiting or eclipses. I know that Uranus sort of spins on its side versus other planets, mergers, crashes, all of that movement. Do you use anything like axes within a 3D model so you can push things together or spin things, or any movement within the models so they can be moved around? Just wondering your thoughts on that.
It's not something we've done too much of yet, but it is definitely something we're thinking about. So right now, our get out of jail free card is to use sonification to represent anything in motion, because you can sort of use surround sound to give people the sense of how something might be orbiting or other things like that. It is definitely something we're going to have to try and crack with this new work that we're doing, where we're looking at those more sort of core physics subjects, particularly if we want to talk about things like the way the Earth and the Sun and the Moon interact with each other. I was talking to one of your colleagues about this earlier today, actually. We have toyed with the idea of maybe introducing something like a sawtooth to a static diagram that would, if you could imagine a line with a sort of like a saw blade 3D print that might promote motion of someone's finger along that line in a particular direction rather than another, to help them sort of create that sense of movement in the diagram. Not sure whether that's going to work, but it's something that we are going to test out. But yeah, I think we might have to be a little bit cleverer. Like you say, have things maybe spinning on axes or have parts of the diagram that can be rolled or moved around as well.
Yep.
I think that will make it so much easier for people to understand. But also something that I'd be really keen to pick your brain about at some stage.
Great. Thank you. Yeah, I'm sorry I'm not there to feel some of the models. But thank you again for your talk.
That's my pleasure.
Questions? Scott got his hand up marginally, but not get there.
Just building on aspects of the previous two questions, you alluded to tactile displays. Does that give you a mechanism for doing dynamics, or I mean, I guess the cost might be prohibitive, but is the technology there?
Yeah, the technology is there. So there are some issues with it though. So the really expensive tactile displays are good because they basically have a series of pins that can be raised to different heights. They do refresh in real time, so you can play movies on them. The only issue there is that you need people's fingers to be in the right place on that screen to actually track what's going on, if that makes any sense. So for particular movies, it doesn't work so well. For something like the moon changing phase, if that's right in the center, that would work fine because somebody could sort of put a couple of fingers over the top of that and feel it. The biggest prohibiting factor with these is that they are relatively low resolution. So they're only, I think the really, really modern ones are a couple of hundred pins by a couple of hundred pins. So you're not getting anything near the detail that you would be with a 3D print. And they're also around about $25,000 a pop. So they're very, very expensive. But the good thing about this kind of technology is the more widely used it becomes, the cheaper that gets. So give it another couple of years and those will be much more affordable. But it's one of the reasons why we've lent into much lower tech stuff for this project, is because we want to make sure that if people want to replicate our work, they don't have to spend a whole lot of money to do it. They can just sort of order some seeds and some balls or find someone with a 3D printer. But yeah, those tactile displays have a lot of potential. It's just something that, yeah, we don't necessarily have access to ourselves. So I haven't had a real chance to play around with those properly.
Excellent. Beck?
Thanks for the wonderful talk, Nick. It's absolutely amazing to see how much this project has grown over the last few years. I wanted to ask about numbers. Do you have any idea of how many people you've engaged with and the impact? How many people have downloaded the 3D prints from your website and things like that?
Yep. So that's all a little bit difficult to track. So we do ask people to let us know when they download the resources, but no one's ever actually done that. It's usually sort of a couple of thousand people per year who access the resources on our website. Whether they actually go in to use them is another question. In terms of our own numbers, so over the last couple of years, we've done a slightly more concerted sort of schools engagement program where the long-term plan with that is to basically be seeing students a couple of times, delivering our different workshops as they progress through their schooling. So far, I think we've seen about 2,000 students, but only about 10% of those are actually vision impaired. So that's just in the last couple of years. And yeah, the feedback from that's generally been quite positive. The really nice thing is we're not noticing anything particularly different between the responses from the sighted students versus the blind students in terms of their enjoyment, how useful they found the tactile resources, whether it's influenced their thoughts on maybe pursuing physics or astronomy as a future career. So yeah, that's kind of nice that we're having the same effect on everybody basically that we're working with.
Yeah. Andrew?
Nick, it's Andrew Prentice here, formerly of the Maths Department. I've recondensed in the Physics Department. It's just about the time you left. And I'm always grateful for that spare desk lamp you gave me, because I have it perched up high in my study when I lose things. And I always think of you when I'm searching for a lost pen or a top to a glue stick. You know, they dry out overnight. Yeah, now the question is coming. Putting the glue stick to one side, the Artemis 2 we've had recently has produced wonderful pictures of the far side of the moon. And there must be so many people who are so keen to learn about that. And I imagine, would you be using light or albedo to bring out the features? That's my question.
Yeah, so that's a tricky one. So this is one of the problems. So we're really lucky in that we landed on galaxies as the initial thing that we wanted to communicate about, because that lends itself really nicely to a direct translation to tactile. The reason for that is when you look at a galaxy where you're seeing brighter stuff, you're generally seeing, well, either brighter starlight or just more gas or more stuff going on. So it does kind of logically map to the 3D shape that you're feeling. The problem with something like the moon's surface, where you've got a lot of light and shadow at play, is that that might not actually translate in a particularly sensible way to a tactile surface. So what we would actually probably be better off doing there is directly modeling the craters and everything else rather than trying to do that light and dark translation. Actually, NASA's already produced, these are quite old now, but there are two really lovely tactile surfaces they've made. One is the near side and one is the far side of the moon. And my takeaway tactile message from those is that the far side has got so many more craters so close together. And so, yeah, you can sort of do stuff like that. But I think for something like a planetary surface, yeah, our model of modeling wouldn't work so well. You would need to probably directly model instead. But I'm sure there are a group in NASA who are doing some really great stuff with tactile diagrams. So hopefully they're on that one. But also, Andrew, it's really great to see you again.
One last question, and then I think we'll wrap up for tea, coffee, snacks.
Hi, this is a great presentation. Have you always spoken to or speaking to the Ausgrav public outreach?
I have not yet, but I would really like to. So
yeah, I think they'll be very interested in your work, and I think like in the previous collaboration wide retreat, I think they've already like shown some like kind of tactile ways to convey gravitational waves, and I think like might be good to share ideas with them.
Yeah, no, I would definitely be very happy to do that. So I know the group at Glasgow have made some extra models on top of the ones that we provided them as well. So they've taken the typical sort of gravitational wave signal and printed it in 3 dimensions, which is actually, it makes sense, right? Because you are actually dealing with 3 parameters in those ones. So yeah, I think, yeah, if I could talk to that group, if you could hook me up, I'd be really happy.